Astronomers have wrestled with this problem for decades. Back in the year 2000, new measurements suggested a star named Methuselah was about 16 billion years old, older than the universe itself, which was thought to be around 14 billion years old. Impossible. A star cannot be older than the universe that contains it. That kicked off over a decade of remeasurement. By 2013, Hubble data narrowed the star's age to about 14.5 billion years, right at the edge of the universe's supposed age, with almost no room to spare. This wasn't a small discrepancy. This was a red flag that never fully went away. Here's the puzzle. When astronomers measure how fast the universe expands today, they get one answer. But look at the cosmic microwave background, radiation from the beginning. Calculate how fast it expanded then. You get a different answer. The numbers don't match. Off by about 9%. In physics, that's huge. We call it the Hubble tension. 2022, the James Webb Space Telescope started looking at the most distant galaxies, the ones that formed when the universe was only a few 100 million years old. What astronomers found shocked them. These weren't primitive, simple galaxies. They were mature, they were big, they had structure. They looked like they'd been around for billions of years, not hundreds of millions. According to our models, they shouldn't exist. They're too old. They're too developed. Something was very wrong with what we thought we knew. But the problems went deeper. White dwarfs, the cores of dead stars, were cooling too slowly. The distribution of galaxies in space had features our models couldn't explain. And there was this mysterious substance called dark matter, which made up most of the universe that nobody could actually detect or explain. For decades, physicists had been patching this model, adding fixes, introducing new concepts. But the cracks kept widening. Something fundamental was wrong with how we understood the cosmos. Imagine you're standing at the bottom of a swimming pool. Light from above ripples and bends through the water, creating patterns of brightness and darkness on the pool floor. You might think those patterns tell you something about what's above the water, but you'd be wrong. They're just light being bent by waves. Now imagine the universe. The light we see from distant galaxies has traveled across billions of light-years of space. Along the way, it passes through matter and dark matter, bending, focusing, refracting. We see patterns in that light. We might think those patterns are telling us the universe is expanding. But what if they're just light being bent along the way? What if light doesn't stay the same? What if it loses energy as it travels? Not through collisions, there's nothing to hit in empty space, but through the Higgs field, the quantum field that fills everything. As light travels, it continuously loses energy to this field, loses energy, wavelength gets longer, and that's exactly what we observe in distant galaxies. Light shifted toward red. Here's the crucial difference. In the standard model, redshift isn't just distance, it's tied to the expansion of space itself. A galaxy's redshift tells you how old the universe was when that light left it, because the universe has been expanding and evolving ever since the Big Bang. High redshift is read as young universe, young galaxy. In this framework, there was no Big Bang, and space isn't expanding. Redshift is simply a measure of distance, how far that light has traveled, losing energy the entire way. A distant galaxy isn't a young galaxy from early in the universe's history. It's just a galaxy that's far away. Its light took a long time to reach us, but that says nothing about how developed, or how old, that galaxy actually was when the light left it. If light loses energy to the Higgs field, where does that energy go? At a certain threshold, when the light energy drops below about 10 to the minus 5 electron volts, the light can't stay as light anymore. It condenses. It transforms. It becomes what we call dark matter. Dark matter isn't some exotic unknown particle. It's photons that have lost so much energy they've undergone a phase change, like water turning into ice. They're just light in a different form. This resolves one of the biggest mysteries in physics. We don't need a new particle. We just need to understand that photons aren't eternal. This creates a cycle. Distant stars emit light. That light travels through space, losing energy. As it loses enough energy, it becomes dark matter. In the cores of stars, that dark matter undergoes reconversion. It transforms back into hydrogen nuclei. These become fuel for new stars. The cycle begins again. The universe isn't expanding, it's recycling. Stars to light to dark matter to hydrogen to stars. An eternal steady-state cosmos. Here's where the theory becomes testable. In the standard model, the cosmic microwave background is a relic, a snapshot of the universe 400,000 years after the Big Bang, when light first escaped a hot, dense plasma. Tired light tells a completely different story. There was no plasma, no last scattering surface. The cosmic microwave background is ordinary light, from ordinary stars and galaxies at extreme distances. that has lost so much energy over its journey that it has redshifted all the way down into microwaves. It isn't a snapshot of the beginning. It's the accumulated, exhausted light of an infinite universe, arriving from every direction. And just like ripples on a pool of water bend light into shifting patterns on the floor below, the matter and dark matter this light passes through along the way bends and focuses it, creating the peaks and valleys we measure in the cosmic microwave background today. The predictions can be calculated from first principles. No free parameters, no fitting, just physics. When we compare the predictions to the actual observations from the Planck satellite, something extraordinary happens. The first peak matches to 99.7% accuracy. The second peak, the third, the fourth, the fifth, all match to within 1 to 3%. The theory also makes a specific prediction about the temperature of the cosmic microwave background. Using only fundamental constants, the speed of light, the electron mass, and the fine structure constant, the calculation predicts a temperature of approximately 2.7 Kelvin. The actual measured temperature is 2.725 Kelvin. The match is 98%. No free parameters, no fitting, just the math working. The theory also predicts what cosmologists call the Hubble constant, a measure of how fast distant galaxies appear to be receding. The tired light prediction is about 72 kilometers per second per megaparsec. Measurements from the distance ladder give about 73 kilometers per second per megaparsec. The match is remarkable. And remember, this wasn't fitted to the data. It was derived from the theory itself. The theory explains other puzzles too. The distribution of galaxies in space, their clustering patterns, the fact that high redshift galaxies look too mature for their supposed age, the cooling rates of white dwarfs. In each case, tired light gives better agreement with the data than the standard expansion model, and in each case, the predictions came from the theory before being tested against observation. To test the theory further, researchers built a sophisticated computer model. They fed it real data about the universe. They modeled how light would bend as it traveled through this universe according to tired light theory. This is a prediction engine. Feed in the current state of the universe, and it tells you what that heavily redshifted, exhausted light should look like by the time it reaches us. In June 2026, researchers ran this ray tracer and looked for anomalies. The algorithm found several candidates. When they checked the location of the strongest candidate, a cold spot at galactic coordinates 209 degrees minus 57 degrees, they found something extraordinary. They had blind rediscovered one of the most famous anomalies in the entire cosmic microwave background, a feature known as the cold spot that had puzzled astronomers for over 20 years. The ray tracer knew nothing about the cold spot. It found it independently as the second strongest anomaly in the sky. The ray tracer also made predictions about two other anomalies in the cosmic microwave background that don't yet have known explanations. These are testable predictions. If they are accurate, it's not accommodation. It's prediction preceding observation. The strongest possible confirmation. This isn't just about adjusting some numbers in a model. This is about the deepest questions humanity can ask. Did the universe have a beginning? Is it finite or infinite? The standard model says the universe exploded into existence 13.8 billion years ago. But tired light says something different. It says the universe is eternal, infinite, a steady state that recycles energy continuously. These are fundamentally different pictures of reality. For 100 years, the dominant cosmological model has shaped how we think about the universe. But science progresses by testing ideas against data. When the data stops matching the model, it's time to look for a better model. That's what's happening here. The test isn't complete. There's more work to do, but the initial results are striking. A theory that was laughed at decades ago is making predictions that match observation better than the standard model. The next decade of observations will test these predictions further. New surveys, new telescopes, new data will either confirm this framework or falsify it. That's how science works. The universe is older than we thought, more massive than we thought, more eternal than we thought, and we're only beginning to understand it. This is the story of a theory that challenges everything we thought we knew. It's a reminder that science isn't about defending old ideas. It's about following the data wherever it leads.